In this lesson, we learn how to do two sample comparisons. There are data that are possibly paired. This is the kind, for example, we observe the blood pressure for one person, but one in the morning and one in the evening. And we have multiple subjects observed. These paired data can be used to compare whether the morning blood pressure and evening blood pressure tend to be same or not. Similarly, in other paired data, we could also do such comparison. Let's say, suppose we care about the height of twins. Both children, twins, they might have something related, and we have measurement from twins. In this case, the measurement from the different person in the same family, the twins, they are paired. And what we care is to see whether the mean of the difference in the pair is equal to a constant or not. So in this case, the sample might be small, might be large. And let's first consider the small sample size case. We have a paired data, and the total number of pairs is n, and let's say this n is small. And we can define the differences of the paired data. Let's say for the ith subject or ith pair, the difference is di. That's simply the difference of those observed value in those pairs in that pairs. We'll treat those paired differences as if that comes from a single sample, and we no longer work with the original observed individual data. So this is one thing to emphasize. The D itself, paired difference, is the single sample. In other words, we only work with the DI, not with the XI1 or XI2. So once we computed the difference, now we are actually really dealing with just one sample. And with this one sample, we can now do the test of whether the mean of these DIs are 0 or mean equal to a given value. And for this case, we do not have the observed standard deviation, and we would estimate the standard deviation of the Ds by using the sample standard deviation of these Dis, just like we did in the one sample test. So the essential nature is the same as the one sample test. And now what you have is the data computed from the pairs. So D1, D2, and the Dn, those are the differences from the pairs. And this becomes the actual data. Paired differences become the actual data. And we're trying to test, for example, the mean of D is equal to a constant, let's say, for example, 0, or versus one of the alternative hypotheses. For example, mu D greater than 0, or the alternative could be the difference has mean less than 0, or the two-sided hypothesis, the difference has mean not equal to 0. We do not have to just test the mu D is 0 or not. We could consider any arbitrary mu 0 to do the test. If you are considering the test to see whether the difference has mean equal to a given value mu 0 or not, then the hypothesis will be specified in terms of the mu 0. So the difference actually represents the mean of the difference in the mean from the two samples. In fact, mu1 is used for the first population's mean, or in the paired sample, and mu2 is the mean from the second population, or the second in the paired samples. And then we are trying to test whether the difference is a given value delta 0 or not. And the alternative hypothesis again is either the upper tilt, like this, greater than or less than or unequal. And the test statistic would be the average from the differences. So basically, if you have already computed the DI, then this difference in the average of the differences minus the value under the null for the mean difference, divided by the standard deviation over square root of n is our statistic. And what is this SD? Here, SD is the sample standard deviation of the differences. Deviation of DIs. Okay, so that's the test statistic, and the p-value will be computed just like in the one sample t-test. If the research hypothesis is upper tailed, means we're testing the mu difference is greater than a given value, that's delta 0. Delta 0, then our extreme would refer to the right of the observed statistic in the t-distribution with n-1 degrees of freedom. So for this one, again, the p-value will be obtained by 1 minus pt with the observed test statistic, and then the degrees of freedom is n-1. That gives us the p-value from upper tailed test. For lower tailed test, the extreme refers to the test statistic too small. So in this case, it would be less than the observed statistic, and that p-value in R can be computed by the pt. And then we put in the test statistic, and then we put in the corresponding degrees of freedom. So that's lower tail test. And for the two-sided test, we will have the both tail giving us the p-value, because when the average from the sum paired differences d bar too large compared to the delta 0 or too small, in both cases it tells us that it's extreme compared to the observed value. So in this case, if you want to compute p-value, you can use twice of the pt, and then we put in the absolute value, negative absolute value of the test statistic. Absolute value is ABS with the parentheses. Okay, that's absolute value. We put a negative because we're looking at just the left tail, and then we upward will multiply by 2. So here the degrees of freedom n-1 also need to put in there. That gives us the two-sided test p-value. And then when we make a conclusion, we check whether the p-value is less than significance level or not. If it's less than significance level, we will reject the null hypothesis and conclude that there is evidence to support the research hypothesis. If we do not reject, we have p-value being larger than significance level, then we say we don't have evidence to reject the null hypothesis. Here's an example. In this example, we want to see whether the firstborn children have higher IQ compared to the second-born children. What we have is a random sample of size 9 taken from US families with at least 2 children. And out of the 9 samples, 9 families sampled, average IQ from the older child is 101, and average IQ from the second-born is 98. And the sample standard deviation in both groups was 15. And furthermore, the standard deviation of the paired differences was 10. We want to do a test of whether the mean IQ of firstborn and secondborn is greater than 0 or not. So research hypothesis, because we wanted to know if firstborn have higher IQ, so then the secondborn, this is the research hypothesis. So we put research hypothesis of greater than. So mu1 minus mu2 greater than 0, where mu1 is the mean IQ for the firstborn children, and mu2 is the mean IQ for the secondborn children. Null hypothesis, we always specify the equal dating. Okay, so that's the hypothesis. And now consider the test statistic. We use the d bar minus the value under the null, which is 0. And we need the SD divided by square root of n. In this case, what is the SD? What is n? The d bar is equal to the difference from the average. So it's 101 minus the 98. That's the d bar. And then the SD, here we have two sentences. One saying that the sample standard deviation in both groups was 15. And the other one says that the standard deviation of the paired difference was 10. What we need is the standard deviation of the paired differences. We do not really care about the standard deviation of single population or single sample. We only care about the standard deviation of the paired differences. So SD here is equal to 10. Therefore, the statistic would be simply equal to this D bar divided by 10 over square root of 9. So that's the sample 10 over square root of 9, and X bar here, D bar is the 3. And then when we compute the statistic, we get the 3 minus 0. 0 is under the null value, okay. And the denominator is the standard deviation estimate based on the sample standard deviation of the D bar. And then this value, test statistic, we will use that to determine the p-value. Since the research hypothesis is upper tailed, so mu1 minus mu2 greater than 0, so we would compute p-value with the upper tail probability. So probability of greater than the test statistic, that's the p-value. For this p-value, we can use 1 minus pt, and then we put in the test statistic. So in this case, you could do it just directly with the 0.9, that's the test statistic, and give the degrees of freedom 8, because sample size is 9. 9 minus 1 is 8. So this gives us the p-value. And with this p-value, after finish computation, you see that 0.1972, that's a value not small. For any reasonable significance level, like 0.1, 0.05, or 0.01, this p-value is always greater than the significance level. Therefore, we will not reject the null hypothesis. So when we don't reject, we say fail to reject the null hypothesis. And therefore, we conclude no evidence to say that the firstborn has higher IQ than the second-born children. So that's this example. We use the average difference from the sample, average paired difference from the sample, divided by standard deviation of the paired difference divided by square root of n as the test statistic. And with t minus t distribution with n minus 1 degrees of freedom to compute p-value. For confidence interval, it's very similar. So we again use the point estimate. We use the sample averages of the paired difference as the point estimate. So this paired differences as the point estimate of the mean difference, and then from there we use plus minus the certain number of standard deviations, standard errors to give us confidence interval. And what do we use for this number of standard errors? This comes from the t-distribution with n minus 1 degrees of freedom. This part is exactly the same as in the one sample confidence interval case. So here, for example, when we use 95%, we consider 95% confidence interval, then this would be the critical value from the t-distribution with the pt, it's qt. It's qt, and you put this 1 minus alpha over 2 there. For example, 0.975 for the 95% confidence interval, and then you put the degrees of freedom. This is for the 95% confidence interval. And this SD is still the sample standard deviation of that paired differences. Okay, so that's the confidence interval. Let's see this example about the firstborn, secondborn, and their IQ. We want a 95% confidence interval for the mean difference of their IQ, firstborn, secondborn children. We already had x1 bar, x2 bar, and sample size and standard deviation from the paired differences and so on. So here, I just put x1 bar a value, x2 bar a value, and n1 at the n and the SD. This SD is for the standard deviation of the paired differences. And then here the alpha, because I want 95% interval, alpha is the error part, 1 minus the 0.95. Therefore, when I need to give the confidence interval, I would just do the x1 bar minus x2 bar, and then put the confidence interval, the percentiles here. You can put a minus or plus, but because these two, as long as you recognize, once you put the two of these percentages there, one is alpha over 2 proportion, the other one is 1 minus alpha over 2. When you put these two there, you will get the two bound, lower bound, upper bound of confidence interval. Just make sure that the smaller one in the result gives you the lower bound, the bigger one gives the upper bound, and then the S over square root of n at the end. So this will give us the computation of the confidence interval in one line. And this QT here give us both of the two of the critical values. So once we finish the computing, our interval can be reported, and we use this interval, for example, check to see whether the mean IQ from firstborn and secondborn children is equal to 0 or not. We just check whether the interval contains 0 or not. If you have a question about why sometimes I do plus, sometimes I do minus in this QT, that's only because here I'm doing both. But if I'm just considering one-sided bound, then I have to be careful. If one-sided bound, I have to use the minus. Okay. Here's another example. Maybe before I move on, I should explain why I have this QT here. In other words, why do I have this plus minus, but I'm just using one of the QT to give us the percentile, the quantiles. So that's because when we try to derive the statistic, we're doing like this, d bar minus the mu of the difference, that mu difference, I'm just going to use mu to represent, and SD over square root of n. This is between two numbers. One is this T's critical value. I'm going to use this 1 minus alpha over 2 and minus 1 degrees of freedom to write that. This is talking about the upper one. Okay, this is for example, 97.5 percentile. And the other side is the T with the corresponding lower side of the percentile. And once I do that, when I try to write it in terms of the interval of mu, I will first multiply SC over square root of n on both sides. So if I do so, the left-hand side give me still the percentile, but it will be multiplied by the SD over square root of n, and the right-hand side will have the corresponding percentile multiplied by SD over square root of n. And then afterward, what I want is the interval of mu, so I have to move the d bar to both sides. So I would subtract the d bar from all three sides in this inequality. So if I subtract the d bar, what I'm going to get is this mu, negative mu, less than this negative d bar, and then plus the t, and then n minus 1 degrees of freedom, and I have SD over square root of n. And the other side, I have the SD over square root of n, and also the minus d bar plus, here's t percentiles. And next, I need to multiply -1 on all three sides. But once you multiply -1, the sign will change. So the interval becomes this is less than, that is greater than, and here's the d bar minus minus 1 here, and I see over square root of n there. And this side is also a d bar. And minus, here is a t alpha over 2, and the n-1 degrees of freedom, and SD over square root of n. So as you see, the interval actual lower bound, upper bound would always be written as d bar minus these t percentiles and times SD over square root of n. Just that when you do the t percentiles, these two t percentiles, t alpha over 2 versus the t 1 minus alpha 2, they are of opposite sign. So they are just symmetric of each other around 0. That's why regardless of I use d bar minus these 2 percentiles or I use d bar plus these percentiles, I will still end up having the same confidence interval, but just need to be careful in the end, what do I get? Which one is lower, which one is upper bound? Here's an example for that. For this example, we are looking at the cedar apple rust on apple trees. And this kind of rust has rust-colored spots on apple leaves. And it's suspected that most possibly that removing these red cedar trees around apple trees could help to reduce these rust-colored spots on apple trees. So they did an experiment. This experiment in the first year of the experiment, the number of affected trees on affected leaves on 8 trees were counted, and this first row of the data give us the number of these rust-colored spots, and in the next row it gives the number of rust-colored spots after those cedar trees have been removed. Any of the cedar trees within 100 yards of the orchard was removed, so that they are hoping that removing that could help reduce the rust. So basically what we have is each of the orchard here, before removing the cedar tree and after moving the cedar tree, so that's paired data. And with this paired data, we would like to see whether there's evidence that removing the cedar trees was effective or not. So for this, what we want in terms of effective, that it means that we are trying to test or doing confidence interval. So if we do a test, we would want to see the mu difference. So mu1 minus mu2, the difference in the research hypothesis to be greater than 0, where mu1, this is for the mu1 is for year 1, mu2 is for year 2. Okay, and null hypothesis would be written as the mean difference is 0. So null hypothesis, we write it as mu1 minus mu2 is 0. And the research hypothesis is the mu1, that's the first year. The mean is bigger than the second year. And when we do a test, we'll use the difference d bar minus the 0 divided by the SD over square root of n, and that's the t statistic. And from the t distribution, we use the 1 minus pt with that t statistic and the n minus 1 to give us the degrees of freedom. And what is the n here? Because we have 8 trees, so the n is actually equal to 8. So that'll give us p-value. Based on this p-value, we make a conclusion. So that's if we do the hypothesis test. If we try to use the confidence interval approach, we would use the d bar plus or minus the t critical value, like 1 minus alpha 2 percentile and minus 1 degrees of freedom, and then the SD of the differences divided by square root of n to get a confidence interval. And with the confidence interval, we try to see whether it's 0, or actually in this case, because effective, we could do one-sided confidence bound. So simply just look at the mu1, mu2, the one-sided confidence bound. We just need to find the lower bound and see if the lower bound is bigger than 0 or not. If it's bigger than 0, that means that it's effective. But if we have already computed to the confidence interval, in that case, we check whether the 0 is inside of the interval or not. So for this one, let's see. We first read in the data, do hypothesis test. Then this D will compute the difference of the two samples, the paired sample. And then afterward, we do t-dot test on D. And the mu0 specifies what's the value for the null hypothesis. If you do not specify, it is always testing for the 0. For this case, since we are testing whether the mean is 0 or not, so it's fine. But if we are testing for mean difference is equal to another number, for example, whether the mean difference is equal to 1 or bigger than 1, in that case, we have to specify mu0 equals 1, okay? And afterward, we specify alternative equals the greater. That will conduct the test for us. We have the statistic here, and we have the degrees of freedom. Degrees of freedom is n-1, and then p-value here, and from there, we make a conclusion. Because this p-value, if we use 0.05 at level, the p-value is less than 0.05, then we would reject the null hypothesis. Reject the null hypothesis. What can we conclude is that removing the cedar trees did help reduce the colored rust. So we conclude removing cedar trees within 100 yards. 100 yards of the orchard did help to reduce rust, reduce the cedar rust. Okay, so that's for this example. It's pretty straightforward. You just need to specify the hypothesis and then use the difference as the data and feed it to t-dot test. Remember to specify the alternative based on the research hypothesis direction. The next part, let's look at the two sample comparisons when we have data coming from two different samples. So in this case, we are really trying to compare two separate populations, and these two populations are unrelated. Their samples are also unrelated. Let's say we have one sample collected from one population, and now we want to compare these two samples together. In this case, there will be different scenarios. The scenario includes whether they have the same variance or they do not have the same variance. And this will lead to the different situation. If the data from the two situations are both having small sample size, in that case, we'll have to make an assumption about the normal distribution on both populations. And then we will proceed again using some t distribution with certain degrees of freedom to conduct the test. As we proceed, you will see that regardless of the variances being equal or not equal, we will have a corresponding t distribution, but the two situations will have different degrees of freedom in the t distribution. The hypothesis in this case will specify the null hypothesis being the mean difference is equal to a given value delta 0, and the alternative hypothesis or research hypothesis we specify it's upper tailed or lower tailed or two-sided. when we consider the test statistic, we will again start with the point estimate of the parameter of interest. In this case, the parameter of interest is mu1 bar, the population mean difference, mu1 minus mu2. And then to construct the test statistic, we'll start with the point estimate of mu1 minus mu2. A good point estimate in the case when data comes from normal is the sample mean difference. So x1 bar minus x2 bar, that's the sample mean difference. This is the maximum likelihood estimate. For like x1 bar is the MLE for mu1, x2 bar is the MLE for mu2, and the invariance principle from the maximum likelihood estimate tells us that the difference is the MLE for mu1 minus mu2. So that's our starting point. And when we try to compose the test statistic, we'll try to use the combine this estimate. So estimator is x1 bar minus x2 bar. And we also have the actual parameter, mu1 minus mu2. We'll combine them together. So the statistic at minus the parameter, the estimator minus the parameter, and then we need to divide by the standard error. Standard error of x1 bar minus x2 bar, just so that this will be properly standardized. For this case, the standard error of x1 bar minus x2 bar, because the two populations are independently sampled, so standard error is simply equal to standard error of x1 bar plus the standard error of x2 bar. And x1 bar would have a standard error if you try, variance of x1 bar plus variance of x2 bar, and they take square root. That will give us standard error. And for variance of x1 bar, that's the sigma squared from the first population, and the variance of the x2 bar is sigma 2 squared from the second population. Okay. The statistic. So originally, if I'm trying to write, this part would be the sigma 1 squared, and this part would be the sigma 2 squared, because those are the variance of x1 bar is equal to sigma 1 squared over the n1. Variance of x2 bar is equal to the variance from the second population divided by n2. But unfortunately, we do not have the sigma 1, sigma 2 available. And if sigma 1, sigma 2, both of them are known and they are different, then we simply use the standard deviations of the first population, sample variance, this part. Sample variance from the first sample to estimate sigma 1 squared, and the sample variance from the second sample to estimate sigma 2 squared. And then this gives us the statistic. This statistic does not have exactly t-distribution, but it's approximately well approximated by a t-distribution. And the degrees of freedom, unfortunately, depend on the standard deviation. So there is a approximation formula. This formula tells that it's a Satterthwaite approximation formula. Tells us that the degrees of freedom for that statistic is equivalent by this one. This is the degrees of freedom. And this degrees of freedom, you can use the sample standard deviation here squared it, sample variance, and then divided by n1. And here's the sample variance divided by the n2, and you square them. And in the denominator, you also have this sample variance divided by n1 squared, and then divided by n1 minus 1, and so on. So that computes the degrees of freedom. We have a test statistic is approximately following a t-distribution with this degrees of freedom. So we can use this t and its degrees of freedom to help us to compute the p-value or confidence interval. So if we do the test, we compute the p-value based on its upper tailed, lower tailed, or two-sided test using the t-distribution with that new degrees of freedom. And afterward, if p-value is less than the significance level, we reject the null hypothesis. Otherwise, we will not reject. We say fail to reject null hypothesis. And if we are trying to construct a confidence interval for the mean difference, we will just use this point estimate here, x bar minus x1 bar minus x2 bar, and then afterward we use plus minus the t percentiles, and then we use the standard error, which comes from this computed estimated standard error from the two sample variances. Again, the t percentiles, we use the t distribution with that new degrees of freedom, and new was that Satterthwaite approximation. Okay, so that's the confidence interval. I did not really put too much detail in deriving this confidence interval. That's because earlier when we learned it, we already know this confidence interval is always given by the point estimate plus minus the distribution percentiles and times the standard error. Okay, so this is the confidence interval when the standard deviations are unknown. And here's an example. For this example, we have a randomized experiment involves 63 individuals, and they were randomly sampled from obese adults in Philadelphia area. So out of these 63 individuals, 33 of them are randomly assigned to Atkins diet, and the remaining 30 were assigned to a conventional diet. At the end of 6 months, the amount of weight loss was calculated. Average weight loss in the Atkins group was 15.42 pounds, and the sample standard deviation of 14.37. So this is from one sample. You have an average and you have sample standard deviation. And for the other group, conventional diet group, the average weight loss is 7.01 and the standard deviation of around 12. And the question is there evidence that one diet was more successful than the other? So for this case, more successful than the other, then we are trying to test whether the mean difference is depending on which one do you use. If this is the mean weight loss for the first group, mean weight loss. Weight loss from the Atkins diet. And mu2 is the other one, then more effective refers to the mu of the first group, mu1 minus mu2 greater than 0. So if you do not use mu1, mu2, you can use mu sub A for Atkins group, mu sub C for conventional group. So that's the research hypothesis. We always put what we wanted to find evidence in the research hypothesis. Afterward, let's compute our test statistic. Sample average has difference given by these numbers. And then the standard errors are, this is the sample variance divided by the sample size, 14.7 square sample variance. And similarly, here's the sample variance from the other sample and divided by the sample size. Finish computing, we get the standard error. And then the t statistic now would be using the difference 8.41 minus the value under the null hypothesis. This is the value under the null. And then divided by the standard error in denominator. This ratio gives us statistic. And since we are looking at this upper tailed test, then the p-value would be 1 minus the pt. Okay. This one actually is for a two-sided. This is not correct. This is a two-sided test. So for this one here, the p-value should actually be given by this one. The p-value should be equal to the 1 minus pt with the 2.5, and then we put the degrees of freedom there. And the degrees of freedom, in this case, I did not really do the calculation by hand. it is computed separately, and then so put p-value 1 minus pt there. And how do we compute this p-value? We simply just use the formula that's on this slide. The sample variance and the sample size combined together to compute this degrees of freedom. Okay, and once we compute the p-value, like in this case, after multiply by 2, it's this 0.015. So actually, p-value would be around the 0.00 or equals. This would be equal to around 0.0075 something. And with that p-value at 0.05 level, we will reject the null hypothesis, conclude that the Aitken diet group is more effective in weight loss. Okay. So if we do it in R for the one-sided test, more effective for the Aitken group, we'll first read in the data, and here is the response variable, the Y variable, the observed data, and then we have the diet here, specified two different diet group, because the data were given as columns, like loss at 6 months, and also have the diet. So you have the data in that loss, with loss at 6 months, and what diet is it? So that's how the data look like. And here we just put a formula and put the diet on the right-hand side. And then this theta test is missing the alternative. I should put the alternative equals greater. And once I put in the correct alternative, I should get the correct p-value, which should be half of this one. Okay, so that's the t-test. If you had the data for the loss after 6 months using each of the diet separately given in X and Y, then you can use theta test X, Y, and then you also specify the alternative to do the test. Compare the weight loss at 12 months. So they also have data, another column that gives the weight loss at 12 months. So if we want to do the comparison here, this time we do 12 months. For this one, I did not do the alternative, and in this case, actually the p-value is big. If you look at this output, this is 0.47. That means consider the two tails together, the probability is almost 50%. So one-sided of that, if you do one-sided test, it will be that thing divided by 2. So still about 24% of probability on one tail. So in either case, at 12 months, then the diet no longer make a difference in terms of the weight loss, the mean weight loss. So at 12 months, the difference is not significant anymore. So that's the example for the two-sample t-test, and we are not assuming that the variance is being equal. If the variances are equal, in that case, it's possible to combine the sum square deviations from each sample and then make a pooled estimate of a common variance. In that case, it will be more powerful. That test will be more powerful. But in order to use that, you first need to make sure that the variances from the two samples, from the two populations are equal. That's not included in this part of the slide. So to summarize, for the two sample comparisons, we have two different scenarios. One scenario is that we have paired data. This paired data comes from double measurements from the same subject, such as the measurement from a person when this person was young, and a measurement for the same person after the person aged for 20 years later. Or consider, for example, a weight loss program, weight management program before participating in the weight management program, the weight measurement, and also after the measurement program. So one person, you have two of the data point. One is before the weight management program, the other is after, and we have multiple persons data being recorded. So each person's two measurements give us the paired data. And then afterward, we use these paired data to test whether the mean difference in the two populations are the same or different, or test whether the mean difference is equal to a given number or not. In this paired data, we use paired difference, average paired difference, minus the value under the null and divided by the standard deviation of the paired difference divided by square root of n to give us the test statistic that has n minus 1 degree of freedom from t distribution to compute p-value. On the other hand, another situation is if we have data that come from different populations that are unrelated. For example, you have subjects in treatment and subjects in the control, and you're trying to compare the treatment and the control, whether the mean difference is equal to a number or not, or the mean difference is greater than something. In that case, we do not have paired data. So in that case, our statistic will be based on the average sample difference, which means the x1 bar minus x2 bar, and then minus the mean difference under the null hypothesis, and then divided by the standard error. The standard error in this case is simply the square root of a term. And what term is that? That's the sample variance from the first sample divided by the sample size, and plus sample variance from second sample divided by sample size. This statistic has approximately t distribution with degrees of freedom given by the Satterthwaite approximation. You compute the p-value based on that t distribution, and again, will reject null hypothesis if p-value is less than the significance level. And if p-value is bigger than significance level, we do not reject null hypothesis. So that's about this two-sample t-test.